All right. Hope you all are doing well today. We're going to continue to talk about op amps, but today we're going to focus more on the application side of things versus just generically being able to analyze op amp circuits. So these are going to be commonly used negative feedback amplifier topologies. And for those of you that are in electrical engineering, biomedical engineering, mechanical engineering, um, and some of the chemical engineering students, these are the ones that you are going to interact with fairly regularly when you are monitoring or setting up sensor networks at manufacturing sites, processing plants, things like that. So the first amplifier circuit that we're going to look at is actually one of the circuits that was in your in-class assignment problem in our last class meeting, but we're going to look at it from a more general perspective. So I'm going to start with the op amp itself. Let me put the inverting input terminal on top like so. And as per usual, I'm going to have some sort of negative feedback path. In this case, it's going to be a resistor RF that is connected between the output terminal and the inverting input terminal. I'm going to put a resistor, let's call it R1 here, connected to the inverting input terminal, and I'm going to ground the other side of this resistor R1. I'm going to apply some input voltage Vn of t at my non-inverting input terminal, and I'm going to take my output here at the output terminal. So my goal here is to develop a generic expression that will tell us what the output voltage is for any given input. So we're kind of looking at the system transfer function as a whole here, okay? So in order to develop these relationships, I'm going to apply that five-step technique that we talked about in our last class meeting, and then we're going to kind of discuss what this particular type of amplifier might be used for. So kicking things off on the analysis side of things, I'm applying op amp rule number one, where I'm observing that no current can flow into either of my input terminals. Rather obviously, the voltage present at my non-inverting input terminal is just going to be Vn, which means there's a voltage of Vn of t here at my my inverting input terminal, because op amp rule number two says that the voltages have to be the same at the input terminals. Now I'm at the point where I'm going to be applying Kirchhoff's current law, so I'm adding this current and this current together, and I'll write that KCL equation over here on the right. So we would have Vn divided by our resistor R1 plus Vn minus V out divided by our resistor RF is equal to 0. And we could algebraically rearrange this guy, and what we would find is that our output voltage is simply our input voltage multiplied by a factor of 1 plus RF over R1. So I'm going to define the closed loop voltage gain of the system, so AVCL. This is just going to be the ratio of our output voltage to our input voltage. And in this case, that ratio is simply 1 plus RF over R1. Okay. I'm just going to make a note here that this guy is what we would commonly refer to as the voltage gain of the system. Okay. So let's talk about what this amplifier is doing. Okay. So if we look at our transfer function or our voltage gain for our system, we can see that it is simply 1 plus, and then it's just the ratio of the two resistors that we use to bias it. So that means that this amplifier is only capable of making input or output signals that are greater than or equal to our input signal, right? So if RF is really small, like a wire, and R1 is really large, like an open circuit, then the voltage gain of this system is simply 1, meaning that our output voltage and our input voltage are the same thing. We would commonly refer to that as a unity gain buffer amplifier. And I'm just going to make a note here. If RF approaches 0 ohms and R1 approaches infinity ohms, AVCL is equal to 1, and this is what we would call a unity gain buffer. And unity gain buffers are very frequently used, particularly in biomedical engineering and electrical engineering applications, where our input signal is generated by a sensor that does a good job of creating a voltage, but that sensor doesn't have a lot of power associated with it. So things like piezoelectric sensors for measuring mechanical deformation and things like that in like prostheses would be something where you would use a unity gain buffer to effectively boost the power of the input signal by replicating its voltage, but allowing current to come in through the power supply terminals of the op amp itself. Okay. So the lowest possible gain that this system can generate is a gain of 1, but it can generate gains that are much larger than 1 by simply making the ratio of RF over R1 something large. So if we wanted to increase the voltage gain of this system, we could do so by either increasing the value of RF or decreasing the value of R1. Notice that our voltage gain is always going to be a positive quantity. It'll never be negative. So this circuit is what is commonly referred to as a non-inverting amplifier. Okay. And this is one of the building blocks of control systems. We use it very, very regularly. Okay. So before we move on to our next circuit, does anybody have any questions? All right. So this next circuit is going to look almost identical. Really, the only thing that I'm going to change here is the location of where I apply my input signal and where I apply ground. Okay. So we're going to have something like this. Once again, I'm going to have negative feedback connecting my output pin to my inverting input pin. I'm going to have some resistor R1 here, but instead of applying ground on the left-hand side of R1, here's where I'm going to apply that input voltage. And then now I'm going to ground my non-inverting input terminal. So, and once again, I'm going to take my output voltage just at the output terminal of the op amp. So if we go through the analysis steps here, we've got 0 amps flowing into or out of our input terminals. By inspection, we can see that the voltage present at our non-inverting input is just 0 volts, since that terminal is tied directly to ground, which means the voltage present at this node is also 0 volts. Applying KCL, we would be adding these two currents together. And so we would wind up getting 0 minus Vn. So I'm just going to call that negative Vn divided by R1. And then we would have 0 minus V out. So I'm going to call that minus V out over RF is equal to 0. And then rearranging this guy, we would get the relationship that V out is simply Vn times a factor of negative RF over R1. And our closed loop voltage gain for this system, which is always just going to be the ratio of V out divided by Vn, would then be negative RF over R1. Okay. So if we look at these circuits, as I mentioned a few minutes ago, they are literally identical. The only thing that has changed is that we've swapped where we applied Vn and where we applied ground on the input side of our circuit. Okay. This simple change causes a pretty appreciable change in the behavior of our output signal. Okay. So we can see that our voltage gain is always negative because RF and R1 will always be positive resistors because those are external resistors that we are applying, okay? So that means if we have a positive input signal, our output will be a negative signal. And if we have a negative input signal, then our output will be a positive signal. So this particular amplifier inverts the polarity of our input signal. So it is called an inverting amplifier. And it is the most commonly used amplifier in existence. Okay. The reason why it's the most commonly used amplifier in existence is because of how versatile it is. So not only can this amplifier boost or amplify signals, meaning if RF is greater than R1, then our output signal is larger in magnitude than our input signal. But it can also be used to attenuate things. So make our output smaller than our input if we ever wanted that to happen, where we would simply need to have RF smaller than R1. Okay. There's not an extra factor of 1 plus anything here either. It's literally just the ratio of resistances. So it is very, very easy to design systems for specific gain values using an inverting amplifier where we don't necessarily care that the polarity of our output signal is opposite that of the polarity of our input signal. Or we could cascade this inverting amplifier into a second inverting amplifier in order to switch the polarity back around. Okay. So this is a very, very commonly used, in fact, it's the most commonly used amplifier configuration that you'll ever see with op amp. So it's used all over the place in all kinds of applications. All right, once again, any questions, comments, or concerns? Okay. So just to recap, these two first amplifiers that we've looked at are how we can make signals larger or smaller than our input signals. And in the case of making them smaller, we're guaranteed to also happen to change the polarity of the signal. Now I want to get into some more common mathematical operations. Okay. So these amplifiers that wind up doing math on signals are actually going to be based on these two topologies. We're just going to make slight changes. Okay. So the first mathematical operation that I want to deal with is just simple addition. Okay. So I'm going to draw a circuit here. Here is my negative feedback path. Here's my output signal measured directly at the output voltage. I'm going to ground the non-inverting input terminal. And then over here on the left, I'm going to have some resistor R1. And I'm going to put an input voltage here, V1 of T. So right now, this is literally the exact same thing as the inverting amplifier. So what I'm going to do now is I'm going to add some more input signals. So if I put a resistor here, let's call it R2, and put an input signal V2 here, and maybe up here we have some resistor R3 and an input signal V3 of T. And I could keep on adding input signals if I wanted to, but I'm just going to leave it at 3 for right now. This amplifier, as we're going to see when we analyze it here in a moment, is actually going to wind up adding these signals together and a couple of other little things, okay? So if we analyze this circuit, we can see that the voltage here is 0 volts, and we're going to simply add the currents that are leaving this node. So this is our KCL at the inverting input node. And what we would wind up getting is negative, excuse me, that should just be a V1, not a VI. So negative V1 over R1 minus V2 over R2 minus V3 over R3 minus V out over RF is equal to 0. And rearranging this, we would find that our output voltage is just going to be negative RF multiplied by V1 over R1 plus V2 over R2 plus V3 over R3, and so on and so forth. So our output voltage is the sum of our input signals divided by those appropriate resistors, and then it's overall multiplied by a factor of RF. So each one of those input signals gets scaled by a different amount. RF divided by the appropriate input resistance, R1, R2, or R3, okay? So this particular amplifier is known as a weighted inverting summer, okay? It is a weighted summer because each individual input signal is weighted or scaled by a different amount. It is an inverting summer because the output signal is of the opposite polarities of the input signals. There's that negative sign out front, and it's obviously a summer because it's adding together those input signals. If R1 were equal to R2 or equal to R3, and we just called this R, then our output voltage would be negative RF over R times V1 plus V2 plus V3. And so we would no longer have a weighted inverting summer. We would just have an inverting summer because all of our input signals are scaled by the same amount. Um, so I'd like to ask you guys a question. Can you think of anywhere where adding signals like this together might be useful? All right, let me ask a different question. How many of you or how many of your parents own a digital bathroom scale? So West says his do. Colin says, he either owns a bathroom scale or his parents do. So this inverting summer is actually how that bathroom scale works. So essentially, I'm going to draw a very crude picture here. So how my bathroom scale works is it's a big rectangular thing, and it's got a spot over here on the left for me to put one foot, and it's got a spot over here on the right for me to put another foot. And each of these places where I'm supposed to put my feet has what's called a load cell. So there's one for the ball of my foot, and there's one for the heel of my foot. And each one of those load cells generates a very small voltage, usually on the order of a few millivolts for every pound that is placed on it. Okay. Those signals are added together and then scaled by the same amount to generate an output signal that is representative of how much the person that the weight of the person that's standing on the scale. This same basic concept is also how the weigh stations that you see when you're traveling across state lines work. Um, so this is basic analog signal processing at its finest. We can just add signals together and then manipulate the output however we see fit. Okay. Um, I didn't give you guys an equation for the voltage gain of this system because it has multiple inputs, and each one of those inputs might be scaled by some different amount. But if we were looking for the voltage gain for just our input signal V1, that's obviously just minus RF over R1. For input signal V2, it's minus RF over R2, and so on and so forth. So each one of the individual input signals gets scaled exactly like we did with the inverting amplifier earlier. Okay. All right, so before we move on to our next circuit, does anybody have any questions or anything? All righty. So we've handled addition. So now let's figure out how subtraction is going to work. And I'll need to do this on the next page. Okay. So starting with my op amp itself, I've got my negative feedback path. So here's, I'm going to call this guy R2. Okay. And then here's a resistor that I'm going to call R1. And here is an input signal, V1. And then on the non-inverting input side, I am going to apply a little resistor circuit here. So I'm going to call this guy R2 as well. And this will be another R1. And this will be V2 T. Okay. And over here on the output, we have V out. Okay. So we looked at something similar to this, actually more complicated when I gave you that really gross looking circuit towards the end of Wednesday's lecture. And then you had something that looked kind of like at least a part of this in our in-class assignment on Wednesday as well. So I'm going to ask you guys for a little bit of help in figuring out what our voltage at the non-inverting input terminal should be. Does anybody have any thoughts on how we might find that voltage I just labeled V plus?
Is it the voltage drop across R2?
It is indeed the voltage drop across R2. How might we find that easily? And it's the same way we did it on Wednesday.
Voltage division?
Voltage division, absolutely right. So this circuit has a simple voltage divider attached to the non-inverting input terminal. So we would just have V2 times R2 over R1 plus R2. That would be our voltage V plus. And then that same voltage has to be V minus. So now we can apply KCL at our inverting input node. And what we'll wind up getting is V2 times R2 over R1 plus R2 minus V1, excuse me, divided by R1 plus V2 times R2 over R1 plus R2 minus V out over R2 is equal to 0. Okay. So I'm going to manipulate this a little bit here. Okay. So let's make this look like V2 times R2. That is a crappy looking 2. Divided by R1 plus R2 divided by R1 minus V1 over R1 plus V2 R2 over R1 plus R2 over R2 minus V out over R2 is equal to 0. So before I move on to a different step, is everybody okay with me kind of distributing that denominator? So now we can make sure I haven't made any errors here. No. Okay. So when let me just put it this way. So I believe that this term right here could be simplified to be V2 times R1 times R2 over R1 plus R2. Then I would have minus V1 over R1. And then I would have V2 times R2 squared over R1 plus R2 is equal to V out divided by R2. Okay. So my two terms that have V2s in them are very, very similar, right? So I have a factor of R2 over R1 plus R2 that's common to both of them. So what I'm going to do now is I'm going to say, so let's see, let me put a R2 over R1 plus R2 out here. Um, let's see. Then I'm going to have V2 times R1 plus V2 times R2 minus V1 over R1 is equal to V out over R2. I think I can manipulate this a little bit further. So let me pull out the V2 term. So I've got an R2 over R1 plus R2. Then I've got an R1 plus R2. So this guy cancels this guy. Minus V1 over R1 is equal to V out over R2. I feel like I've made a mistake in my algebra somewhere, like I'm missing an extra factor of R1, or I've got an extra factor of R2. Sorry, let me look back through this really quickly. So V2 times R2 over R1 plus R2. That's just from voltage division. That part checks out. Minus V1 divided by R1. Okay. Same voltage minus V out divided by R2 is equal to 0. That bit checks out. That put that R1 up in that numerator. That makes sense. That didn't get affected. That put an R2 in the numerator, which makes sense. Move that guy over. Pulled out R2 over R1 plus R2, leaving behind V2 times R1 plus V2 times R2. Left that guy alone, left that guy alone. Pulled the R1 plus R2. Nothing's jumping out at me, so let me just continue on with this algebraic stuff here. So let me think about this. So I've got V2 times R2. I'm going to multiply both sides through by a factor of R2, so that's going to put an R2 squared here. That's going to look like V1 times R2 over R1 is equal to V out, which isn't quite what I'm expecting. So I've got to have some error somewhere in the derivation, so I can't really find it. Um, I could analyze this using superposition, and I could show you pretty easily that we should get the relationship V out is equal to R2 over R1 times V2 minus V1. I'm not entirely sure where the heck the algebra got away with me or got away from me. So I apologize for that. Maybe it's just one or two more manipulation steps that I'm forgetting here. But I know that this is how it should behave. Um, and you would get this exact result using superposition. So I'm just going to put a box around this and apologize for messing up the algebra in some way, shape, or form. But the gist of this circuit is our output signal is just the difference of our two input signals, and then it's scaled by a factor of R2 over R1. So this is how we perform the mathematical operation of subtraction. Uh, and we also have some amount of scaling involved as well. If all of our resistors were identical to each other, so R1 and R2 were the same thing, our output voltage would literally just be the difference of our input voltages, so we would just have direct subtraction. So this particular amplifier is what is commonly referred to as a differencing amplifier because it amplifies the difference in our input signals. I'm still annoyed that I lost a factor of R1 somewhere, but anyway. So sorry about the confusing derivation where I just jumped ahead and gave you the answer, but the algebra is just more than my peon brain can handle right now. So um, I'll try to find it in my old notes and just upload that for anybody that's interested, which I'm assuming is practically none of you, but whatever. All right. Any questions on at least the output behavior of the differencing amplifier?
Does the those two R2s, do they have to be the same resistance value?
So I think um, as long as the ratio of R2 over R1 is the same, it would work, but I'm not 100% on that. So I think having perfectly matched R2s and perfectly matched R1s would be the best case here. Because I know if the two R2s are the same and the two R1s are the same, it will come out to be this. If the ratio of this guy over this guy was the same as the ratio of R2 over R1 that's connected on the inverting side, I think it will work out that way, but I'm not 100% sure. I've only ever really seen it implemented with matched resistors. If all of the resistors have different values, it's still going to wind up being a subtraction of the input signals, but each input signal is going to be scaled by different amounts. And so the math gets really gross really quickly. Um, so usually you wind up using matched pairs of resistors. Any other questions? Again, sorry the derivation got away from me. All right, so we've done addition And we have fumbled our way through subtraction, or I have fumbled our way through subtraction. Multiplication and division can't be done with a single op amp. So now we're going to move on to calculus, and I'm going to show you guys how a single operational amplifier can be used to either take the derivative of an input signal or integrate an input signal. And these two circuits are also very, very common as part of communication systems and control systems and all of that kind of good stuff as well. So you'd be surprised how often it is useful to be able to integrate a signal particularly. Okay, so I'm going to introduce these circuits using only resistors and capacitors. They can technically also be done using resistors and inductors, but in practice, capacitors are used because the tolerance on a capacitor is usually smaller than the tolerance on inductors, meaning that you won't introduce nearly as much error if you use capacitors versus inductors. So I'm showing you the capacitor version because that's the one that you're actually going to see in real life the majority of the time. So before I draw these two circuits, I want to remind you of the capacitor relationships, right? So we know that the current flowing through a capacitor is C times the derivative of the voltage drop across the capacitor. And transversely, we know that the voltage drop across a capacitor is 1 over C times the integral of the current, excuse me, flowing through a capacitor. And I'm choosing to use the integral that starts at negative infinity to make the math a little bit easier to follow so that we don't have to worry about initial conditions on our system. Okay. So the first circuit that I'm going to look at is this guy right here, and it's going to look incredibly similar to our basic inverting amplifier, except that I'm going to replace one of the resistors with a capacitor. So let's start with this circuit where I'm going to have a resistor in the feedback position. So let's just call this guy R. I'm going to put a capacitor here, call this guy C. We're applying our input signal here, and we're grounding our non-inverting input terminal. Okay. All right, so we know that this current is 0 amps and this current is 0 amps. We know by observation that the voltage present at our non-inverting input terminal is 0 volts, which means the voltage here at our inverting input terminal is also 0 volts. And I'm going to do something ever so slightly different here. So I'm going to call, actually, let me use purple. This voltage will be our capacitor voltage, and this current will be our capacitor current. So I'm just defining the current as flowing into the positive polarity terminal, okay? So I'm still going to wind up doing KCL here, but I'm going to say that my capacitor current is flowing in, and this current right here is flowing out. So my KCL equation is going to look like IC is equal to, is equal to negative V out divided by R. So before I move on from this step, is everybody okay with me slightly changing how I'm applying KCL? So instead of saying all of the currents flowing out of the inverting input node add together to make 0. I'm simply saying the current that flows into the inverting input node is equal to the current flowing out of the inverting input node. All right, so what I can do from here is so why is it, Trevor asked, why is it negative? So on the right-hand side, it's negative because we have 0 minus V out. So the current that's flowing up and to the right through our feedback resistor starts at this node right here, which has a voltage of 0. So when we write these expressions for current, we're using the same rules as we did when we were performing nodal analysis. So it's the node the current starts from, which is 0, minus the node it's flowing to, which is V out, divided by R. Okay, so I'm just going to rearrange things here really quickly. So I'm going to put V out on this side, and I'm going to multiply both sides through by a factor of negative R to get rid of that denominator. So I would have negative R times my capacitor current. Well, if I substitute in my equation for my capacitor current up here, I'll wind up with minus RC times the derivative of the capacitor voltage. So now I need to figure out how the capacitor voltage relates to my input voltage. Okay. So in order to make this a little easier to understand, I'm going to draw my input signal as a full-on voltage source, like so. Okay. So the positive polarity terminal of my capacitor voltage is at the same node as the positive polarity terminal of my input signal. And the negative polarity terminal of my input signal is at ground. Well, the negative polarity terminal of my capacitor voltage is at 0 volts, which is essentially ground. So from this, we can see that Vc of t, our capacitor voltage, and Vin of t, our input signal, are actually the same thing. So that allows me to write that the output voltage is going to be negative RC times the derivative of Vn with respect to time. So this particular configuration where we have the resistor in our feedback network gives us what's called a differentiating amplifier because we have our output is a scaled version of the derivative of our input signal. Okay. So if I want to make this an integrating amplifier, all I need to do is swap the position of our resistor and capacitor. Okay. So the circuit that we're going to look at now is, let me do it on a different page. The same thing, except that R and C are swapped. So here is my capacitor and my feedback position. Here's my resistor R. Here's my input signal Vin. And once again, I'm going to ground my non-inverting input node. V out is going to be over here. And I'm going to define my capacitor voltage with this particular polarity, and my current will flow in this direction. Okay. So now let's analyze this guy. So we've got 0 amps flowing into either of our input nodes. I believe that by inspection, we can see that the voltage present at the non-inverting input node is 0 volts, which means this voltage at the inverting input node is also 0 volts. And once again, I'm going to write my KCL equation such that the current flowing into the inverting input node is equal to the current flowing out. So that's going to look like Vn minus 0 divided by R is equal to IC. Okay. So now we've got to figure out, well, how in the heck does this relate to our output signal? Okay. So I'm going to draw my output in this way, just so that we're very clear that this output signal is measured with respect to ground, which I've harped upon in class on Wednesday at numerous times. So drawing it this way, what we can observe is that the positive polarity terminal of our output signal is at this node, and the negative polarity terminal of VC is at the same node. We can also see that the negative polarity terminal of our output node is at ground, and the positive polarity terminal of VC is at 0 volts or ground. So it seems to me that V out is just negative VC. So they have the same voltage but opposite polarities. So using that relationship that V out is equal to negative VC of t, and using our integral based relationship up here, let me find it. VC is equal to 1 over C times the integral of our capacitor current. That's going to give us negative 1 over C times the integral of IC. If we substitute in our relationship for IC, that's going to look like negative 1 over C times the integral from negative infinity to t of Vn over R. And now I can simply pull that factor of 1 over R outside my integral because it's a constant, giving me the relationship V out is equal to negative 1 over RC multiplied by the integral from negative infinity to t of my input voltage with respect to time. So this particular circuit integrates our input signal, scales it by a factor of negative 1 over RC, and gives us our output signal. Okay. So this is an example of an integrating amplifier. And as I mentioned earlier, it's used in control systems and communication systems very, very regularly. Okay, so those are the 6 different types of negative feedback op-amp circuits that I wanted to talk about with you guys today. With regards to your in-class assignment, technically speaking, there isn't one. Usually, we have a mini lab after this lecture when we have an in-person class, and that particular mini lab takes the overwhelming majority of an hour. So there's not really time to do an ICA on that particular day. If you were interested, you could rework Wednesday's in-class assignment by trying to identify which kind of circuits I gave you and then use the voltage gain relationships to analyze those circuits. And you would actually find that that ICA is much, much easier if you can identify those circuits. But if you don't want to do that, that's or that's okay with me as well. So I don't really have anything else that I wanted to talk about today. So if you guys have any questions, I would be more than happy to answer them. And if not, enjoy your weekend, study up and all of that kind of good stuff. If you have any questions about things over the weekend, it's probably better to text me to get my attention because I am notoriously shitty at checking my email over the weekends, but I would be more than happy to answer any questions that you might have, over Zoom, over text, or whatever. So yeah,
I have a question, but it's on the one of the test packets.
sure.
So it's the obviously exam 2 fall 2020.
Exam 2, fall 2020. Which problem can I help you with?
Question 6. I don't understand why it's not 8.4 volts.
Okay, so we are finding the Thevenin equivalent voltage. Um, I'm trying to think of the easiest way to do this. So the Thevenin equivalent voltage is going to be the voltage across this diagonal, essentially. Um, let's do nodal analysis, and now I'm trying to decide where I want to put my ground. Um, Part of me wants to put it at terminal B, but the other part of me wants to put it on the bottom of the 11 ohm resistor. If I put it on the bottom of the 11 ohm resistor, then
VA will equal 8 volt,
yeah,
8.4
VA
volts.
will be equal to 8 volts. And I won't have to do KCL at node A at all. But I will have to do KCL on the top right, and I will have to do KCL at the one that's currently labeled B. If I put it at node B, then if I can figure out what VA is, then I have my Thevenin voltage. So that's where I'm kind of at right now.
Okay. So I guess my biggest problem with it is if it's at if you put ground at B, VA just wouldn't be 8.4 volts because it's shared between the two.
Yeah, so if we put ground at B, so let's work it that way. So and that'll help explain why it's not just 8.4. Okay. So there's our ground. I'm going to identify my nodes here. So I'm just going to keep this guy in green. Then I'll have this guy up here. I'll have this guy and this guy, right?
Yes.
So I have a supernode that doesn't contain ground. So I'm going to have, oh, actually, let me label some things here. Um, so let's call this guy C and this guy D. Okay. So I will have the relationship 8.4 volts is equal to
A minus
VA
D. Yeah.
minus VD. And then I'll need to write a KCL equation for supernode AD. So let me just do this KCL at supernode AD. And so that's going to be this current plus this current. The reason why I'm not including the 11 ohm resistor is because we would have a current flowing down through the 11 ohm resistor, but also a current flowing up through the 11 ohm resistor, and they'll cancel each other out. So essentially, anytime that you have a voltage source in parallel with a resistor as your supernode, you can just throw that parallel resistor away because the currents are going to cancel each other out. So that's going to give me 2.1 amps plus VD over 7 ohms is equal to 0. And now I'll need to write a KCL equation at node C. So that's going to be this guy plus this guy plus this guy. So that would be negative 2.1 amps plus, I'm going to be lazy here, VC over 8 ohms in parallel with 5 ohms. Or I could do VC over 8 plus VC over 5, but it's going to come out to be the same thing. This is equal to 0. And if I solve this system, then my Thevenin voltage is just going to be whatever I get for VA.
Yep, okay. Yeah, I was just hoping that in this situation it'd be the same voltage for A and D, but I guess it's not.
Nope. That 7 ohm resistor that there at the bottom middle messes it up.
All right, well, thank you.
Yep. Any other questions?
Um, not not really. I'm going through it pretty well.
Okay. Carter asked if the test is going to be offered on Thursday last time. It wasn't offered on Thursday last time. It was offered on Monday and Tuesday, and it will be offered on Monday and Tuesday of next week as well. So it'll be the exact same thing where there will be a Monday afternoon offering, a Monday evening offering, a Tuesday afternoon offering, and a Tuesday evening offering.